So it's 11:10, so let's get started. So as you guys know, Professor Mark Davis is out of town to receive his prize contributing to modern observational cosmology. So today I'm giving a lecture for him. Probably some of you guys know me, and some of you guys don't know me. I'm a GSI, one of GSI's, so nice to meet you if you didn't see me, and nice to meet you again if you saw me in section. So today, we will talk slightly more about main sequence stars, and we will focus on the later evolutionary stage of the stars. So before start with the stellar evolution, so we ended the last lecture with this plot. Do you remember this plot? So unfortunately, I don't have laser points. So x-axis is the age of the sun, and the y-axis is the luminosity. So you see the luminosity changes as time evolves. So at the beginning, the sun changes the luminosity very quickly for a short time. And during the main sequence era, so this flat, I don't know, I can use my, so during this era, the sun gradually increases the luminosity for a long time. And at the end, the luminosity changes very crazily. So during the main sequence, sun is quite stable, and also the evolution is very gradual. But at the end, the evolution happens very quickly, and a lot of things happens for quite a short amount of the time. So let's focus on this part. So before the sun stays on main sequence, it contracts and it becomes the sun. So the luminosity changes very quickly, and it starts with lower luminosity than now. So it's about half brighter than now. So it means the sun was quite fainter than now. That means what happens to the temperature of the universe, the Earth? Can you guess? So if the sun was faint, then what happens to the temperature of the Earth? Yeah, the Earth is colder. So we can guess the Earth was cold, but actually Earth wasn't frozen, or Earth didn't freeze at the beginning. Then why didn't Earth freeze at the beginning? Even though the luminosity of the sun is very low. Yeah, because of the carbon dioxide, the Earth could be warm, even though the brightness of the sun is very small. So even though the sun is not very luminous, due to the greenhouse effect, the Earth was quite warm. So at the beginning, Earth has a lot of carbon dioxide. But later, because Earth has ocean, Earth has water, so those carbon dioxides are dissolved in the water. So now we don't have as much carbon dioxide as before. So at the beginning, we had very high greenhouse effect, so the Earth wasn't frozen. So Earth was just there without freezing. So from the previous plot, we see as time passes, the luminosity changes. So as star evolves, the luminosity changes. Also, the temperature changes. So the location of the star on the HR diagram, do you remember HR diagram? So HR diagram is x-axis is the temperature, and the y-axis is the luminosity. So the location of the star on HR diagram is different when the stars are in different evolutionary stage. So using HR diagram, we can guess the age of the star. So especially we use HR diagram to find out the age of the stellar clusters. So I'd like to remind you there are two star clusters. Do you remember two star clusters we learned last lecture? So one is globular cluster, and the other is open clusters. So globular cluster, the star is mostly old. So they are almost all stars in globular clusters are old, and they are red. And there are many tons of stars, and the shape is about quite spherical. But open clusters, they have young stars, relatively young stars compared to the globular cluster, and there are only a few thousands of stars. So compared to globular cluster, open clusters have small number of stars. And also the globular clusters, all the stars form almost at the same time, so the age of the stars are quite similar. But the open clusters, the age of the stars are very different. So the range of the age is various, wide. So let's see how we use the HR diagram to calculate the age of the stellar cluster. So here is the HR diagram. So you see this yellow arrow. So as time passes, you will see how this HR diagram changes. So let's assume these are all stars in one open cluster. And as time passes, from the more massive stars, they start to leave the main sequence. So by looking at the HR diagram, so let's say when we observe the open cluster, we assume open clusters have almost all kinds of the stars, like OBA, FGKM stars. But when we observed that open cluster, we didn't see any like O and B stars. So O and B stars left main sequence. So that means if we use the stellar evolution model, the age of this stellar cluster is between 10 to the 8 to 10 to the 9 years old. So it's about 100 million to billion years old. So by looking at the clusters, if there is no O stars, B stars, or A stars, then that stellar cluster is older. But that stellar cluster doesn't have only O stars, then that stellar cluster is quite young. So by looking at what kind of stars are not on main sequence, we can estimate the age of the stellar cluster. Does it make sense? So this HR diagram, so just by plotting on HR diagram, we can estimate the age of the stellar cluster. So HR diagram is useful to measure the age of the star. So are you convinced we can age the stellar clusters by using this method? For me, it's quite convincing. And so people measure the age of the globular cluster using HR diagram. So the oldest globular cluster is about 13 billion years old. So 13 billion years old means the age of the oldest globular cluster is almost as old as the universe. So some people use globular cluster to study the early universe, or to learn about the history of the universe. Maybe we can guess, because there are many old stars, probably there is some civilization near old stars. Then, like, if you see those extraterrestrial life, then what would you say to them? Like Contact. Some of you guys watched the Contact. Did you watch? So, but still, we don't find any like extraterrestrial life, and we are still looking for extraterrestrial life. By SETI, it's kind of one project to find extraterrestrial life. Anyhow, so let's go back to stellar evolution. So what are main sequence stars? So we have the question in the problem set, right? What are main sequence stars? What is the most important property for the main sequence stars? Hydrogen fusion. So for main sequence, hydrogen fusion is the most important. Thank you, that's good. So there are two processes. So one is PP chain, the other is a CNO cycle. So both processes just generate helium. So basically four hydrogen are converted to one helium. But these two processes happen in different mass of stars. So for low mass stars, PP chain happens more frequently. I mean, PP chain dominates, but in massive stars, this CNO cycle dominates to fuse hydrogen into helium. So what do CNO in this fusion? So CNO don't change their status during the process. So they are just used as catalyst. So CNO just kicks in whole process. So they have hydrogen to fuse into helium. So this happens in more massive stars, and this makes fusion happen more quickly. So why this happens in more massive stars, but it doesn't happen in lower massive stars? So why, like CNO cycle, can you guess why CNO cycle doesn't happen more in lower mass stars than in high mass stars? That's good answer. So to fuse hydrogen into helium, they need to get over electromagnetic repulsion. So the CNO, because this process has CNO in the process, so they need to get over higher electromagnetic repulsion to have this process. Because CNO is our heavier element, that means they have more charge. So they need to get over higher electromagnetic repulsion, so it needs to move very fast. So you need to, this fusion can happen only higher temperature environment. So if the star is hotter, then this process can happen better. So the more massive stars have this CNO cycle. So if you see, so sun has the sun in the sun, this hydrogen fusion happens via CNO cycle is only 10%. But if you look at more massive stars, then hydrogen fusion happens via mostly CNO cycle. So in the sun, most hydrogen fusion happens through PP chain, which is just nothing is involved, just proton is converted to helium by themselves. So summarize what happened to the main sequence stars. So main sequence stars, as we said, hydrogen fusion happens, they are main sequence stars. So this hydrogen fusion happens only at the core, not entire the star. So only the core temperature of the star is high enough so that the fusion can happen. So if the core of the star, the hydrogen is used up, so almost everything is helium at the core, then they leave main sequence. So we can guess how much time these stars spend on the main sequence. So stars like Sun spend about 10 billion years on the main sequence star. So that means Sun can fuse hydrogen to helium for 10 billion years at the core. So this fusion happens at the core, I'm emphasizing. For lower massive stars, their fusion happens slowly. So the fusion happens slowly so they can spend more time on main sequence. So they fuse hydrogen for a longer time than Sun. So they stay about 20 billion years on main sequence. But more massive stars, they can fuse hydrogen more quickly than sun. So they use up hydrogen very quickly, so they leave the main sequence very quickly. So they stay about 10 million years, so like about 1,000 times shorter than the sun. So these more massive stars live on the main sequence shorter time than sun. It's about 1,000 times shorter. But all stars go through this main sequence time era. So if all the stars use up the hydrogen at the core, what happens next? So most of the hydrogen becomes helium at the core. Does helium start to fuse, or what happens? So at the core, all the hydrogen start to be helium, and the hydrogen burning only happens around the core. So we call this hydrogen shell burning. So around the helium core, there is hydrogen shell burning, but the helium is just sitting there. So helium is not converted to heavier element at this stage. So right after the main sequence, after using up all hydrogen, the helium is sitting at the core. But the outer part, hydrogen is burning. We will see the animation a bit later. So now hydrogen is converted to the helium, and this outer part is hot enough to fuse hydrogen, so there is hydrogen burning. But this helium is just sitting here. So this center doesn't generate any more pressure, so no fusion happens. So it starts gradually contract. And this hydrogen burning shell hits the envelope. So this star can get bigger and bigger. So we can see this diagram here. So let's see. So this is during the main sequence. So we have hydrogen burning core and just normal hydrogen. And later we have helium core, and around the helium core we have hydrogen burning shell. And this part can get heat up by this hydrogen burning. So because it absorbs a lot of heat, it expands. The envelope part expands. So it gets bigger and bigger. Also, this hydrogen burning shell creates helium more and more. So this core grows. So it doesn't have any pressure support, but it gets bigger and bigger and more massive and more massive. So the gravity gets dominated. So this core starts to shrink. So at the beginning, when we talk about the hydrogen burning, the star shrinks by gravity so that they reach some temperature to fuse hydrogen, right? So this core also shrinks, and it gets hot and hot. It gets hotter and hotter by gravity. So this core shrinks, and the gravity heats up this core. So here is some summary. So during hydrogen shell burning phase, the envelope part gets bigger and bigger. So let's assume you are sitting on the surface of the hydrogen burning shell, then the sky is getting higher and higher, but your ground is getting lower and lower. So like the difference between your bottom and the top gets bigger and bigger. That's what is happening in this stage. So this stage we call red giant. So why is it red? So it gets bigger and bigger. Then it uses up the old energy to make it bigger. So when it gets bigger, so that the temperature drops. So the outer part, the temperature is low. So the temperature is low means it's red. The lower temperature is corresponding to red, and higher temperature is corresponding to blue. So the energy is used up to expand. So this outer part temperature is about 2 to 3,000 Kelvin. So it's red, but it is expanded, so it's very big. Yeah, core is shrink, but we see the outer part when we observe this star. No, right, outer part. So we see this cooler outer part. So the star is very red, but also it's very big, so it's giant. So overall, it's very luminous because even though it's cold, so the temperature is low, but because the size is so big that it's very hot. So we call this red giant. And one interesting thing is that this outer part is convective. Convective means like boiling water. So the hot blob goes up to the top, and the warm or hot blob, the cold blobs on the top sinks into the bottom. So it has some boiling motion. So like a water, so there is because heat, and so like we have water here, and there is a gas. So this heat of the water, so we have like convective motion at the envelope. So the red giant has some convective motion at the envelope. And also it's very big. So now this part, it was, at the beginning it was this much size. Now it gets bigger. Then what happens to the density in the outer part? So the material is just there, but it only gets bigger. The density drops, or does the density go up? Yeah, the density drops. So this part is very dilute. The density drops, so they are weakly bound to the gravity. So stars can hold this material very loosely. So this part can be easily lost. So about 20% of the matter just is blown up. So like it's kind of wind. So the star loses this outer part. Then next part is supergiant, but this supergiant happens to this supergiant stage. Only the massive stars can go supergiant stage. Layer of supergiant. Let me correct. So after this stage, so helium core shrinks and shrinks. So if it reaches the temperature 6 times 10 to the 8 Kelvin, then the helium fusion can happen. So helium fuses to carbon. But if there is not enough mass, then this core just shrinks, and then it will be degenerate. We will talk about degenerate state later, but I guess you guys heard about degeneracy pressure a few times in previous lectures, right? So even though the core shrinks, if nothing happens, if no fusion happens, then this core becomes degenerate and becomes hydrogen and helium white dwarf. But if there is enough mass, so if the star starts with 0.8 solar mass to 8 solar mass, so it's pretty reasonable range. So the sun is in this range. Then this core shrinks, and then eventually it reaches 6 times 10 to the 8 Kelvin, so it can reach the temperature to fuse helium to carbon. So there is fusion again at the core, so it generates heat. So if there is some heating, then what happens to the star? Is there gravitational contraction, or does the gravitational contraction stop? So when fusion starts, so if the star starts to heat up, then does the gravitational contraction is the core contraction happens continuously, or the core contraction stops? The core contraction stops. So as soon as the fusion kicks in, the core contraction stops. So the star can be stabilized. So like a main sequence stars. So there is helium fusion. So the star is more like stable. So for massive stars, carbon fuses into oxygen. So now this helium becomes carbon, and there is again helium burning shell. So when helium becomes carbon, to fuse carbon also need to reach some temperature. So, but carbon and oxygen fusion happens almost simultaneously. So we have carbon and oxygen core. So there are two stages. When helium is converted to carbon and oxygen, then some stars go to white dwarf having a carbon and oxygen core, or more massive stars go to another stage. So if they are more massive than 8 times solar mass, if the star is more massive 8 times than sun, then the cycle is repeated. So the cycle repeats itself. So oxygen is converted to heavier element, neon, and neon is converted to magnesium, and it is converted to up to iron. So if star is less massive than 8 times the mass of the sun, then after creating the core with the carbon and oxygen, they stop. And then carbon and oxygen core start to shrink because there is no heat support. So the core just collapses by gravity. So there is like a gravitational contraction. So this core starts to shrink. But even though this core shrinks, they can't reach the temperature to fuse carbon and oxygen. So eventually, this core becomes degenerate. So that they are also carbon and oxygen white dwarf. So we will come back to white dwarf later. So only for more massive stars, after oxygen, the more fusion happens, and this process happens like when the fusion happens, the star is stable because this thermal pressure balances out the gravity. But when the fusion stopped, the gravity wins, so the core starts to contract. So we can see this supergiant on the HR diagram too. So this giant, the envelope has envelope gets bigger, but the core gets shrinking. So envelope is still cold. So the giant phase, the envelope expands. So this envelope uses up the energy. So the envelope gets colder and colder. So we see this giant at the right side of the HR diagram. And the temperature, the luminosity is big because the temperature is low. So we see on the right side, and the luminosity is big because these stars are very big. So even though the temperature is low, the luminosity is high. So we see these giants are on this top. So the outer part, again, if there is something burning on the shell, this outer part gets more thermal energy, so it expands, so it gets colder and it gets bigger. And also it loses this outer material. Are you guys following this? So this is for the more massive stars. So more massive stars fuse all the material up to iron. So this process continuously happens. So if it is colder, it should shrink, but this part keeps generating heat. So this gives the energy to the outer part. So it gets hotter and harder. So that's why it expands. But at some point, even though it's very big, it's balanced out by gravity and the heat source. So why does the star stop fusing beyond the iron. So iron is the last material to fuse in star, because iron is most bound element. So iron is the most stable element. So by fusing to heavier element up to iron, you will gain the heat. So the heat is generated so that the star can be stabilized. The star can obtain the thermal pressure. But after the iron, if you want to fuse to heavier element, heavier element than iron, then you need energy. So to go to heavier element, you need energy. So there is no more heating source at the core, so that the star cannot be stabilized by thermal pressure. So iron cannot fuse because it needs more energy. So the iron core just shrinks, because even though it reaches very higher temperature, it can't fuse because the fusion doesn't generate any thermal pressure. So it just keeps shrinking. So it shrinks until it reaches the degenerate state. So we talked about degenerate state a lot. So we will talk about degenerate state a little bit later. But just to summarize, we can see the animation. So let's start with this carbon core star. So this is very massive star, so we can evolve to later stage. So the carbon and oxygen core evolve. So start with the carbon core, and you see on the bottom, the outer part expands. And when the oxygen core, when oxygen core sets in, then now the stars become normal. It's like, so let me show again. So it begins. So until oxygen fusion happens, the star gets bigger, and when oxygen fusion starts, then the star becomes stabilized, so it sustains the normal size. And then when the core becomes all oxygen, and if there is no more fusion, if there is no more. So now you have like inner oxygen core, and around the oxygen core, there is carbon fusion, and around the carbon fusion shell, there is helium fusion, and around the helium fusion shell, there is hydrogen fusion, and there is just a non-burning hydrogen. So like stars become like an onion. And if it is more massive, then the oxygen core shrinks, and then later oxygen fusion happens, and then neon core there is neon core that's in, and the neon core shrinks, and then again this core fuses to magnesium, and it happens consecutively, and then later it has the iron core inside, and it has different shells of the different burning shells of the elements. Different elements burning shells. So the star becomes like an onion. So inside there is iron, and going outside there is a different shells burning different material, different elements. So at this stage, the iron core starts to shrink because iron can't be converted to heavier element. So there is no more thermal pressure support. So this star will die. So iron core shrinks, and other parts will blown up. So this is supernova type 2, and this is one of the stage of the death of the star. So we will come back this part probably next lecture. Does it make sense? Are you guys following the evolution of the star? But this is for the more massive case. But if we look at the sun stops at the carbon and oxygen core. So we can see how sun evolves here. So hydrogen burning shell, and it gets bigger and bigger, and it becomes red giant. And when helium starts to burn, it is stabilized, so it's not very big. It's the gravity and the thermal pressure is balanced. But again, this helium becomes the oxygen, and this oxygen core just shrinks, and there is no more thermal pressure balances out the gravity, so it just shrinks and becomes white dwarf, and this outer part is blown up. So we see this tiny, tiny white dwarf. White dwarfs are supported by degeneracy pressure. Then we have heavier elements than iron in the universe. Then where those heavier elements come from? How those heavier elements created? Just talk to your friends and do about like 30 seconds. Show the color answer. Please show me the color answer. Are you guys now? Do you know the answer? Like, did you decide? Could you hold the color? What you think? Yeah, we didn't learn about supernovae, but there is supernovae explosion. So by explosion, the heavier elements are generated. So we will come back about this stage later. So I kept talking about the pressure. So the normal stars are supported by the thermal pressure generated by the fusion. So if there is fusion, it generates a thermal pressure. The star can be balanced between the pressure and the gravity. So like this balloon, so if the fusion heats up, then the gas particles are moving very fast. That creates the pressure. So you may think about heated balloon, and that's kind of star. So thermal pressure is the most important force to balances out the gravity for the normal stars. But later, if there is no fusion, then just due to the gravity, the core shrinks, or the star shrinks, so it gets compressed. As it gets compressed, it gets more dense and dense. So if you push the things, and then it gets denser and denser. But as it gets denser, it gets hotter and hotter. But we let it there, and then it will cool down. So we wait for cooling, and then just makes it shrink, makes it small, so that we make this very, very dense. Then eventually, the quantum mechanics becomes very important. So at this point, degeneracy pressure becomes important. So to talk about degeneracy pressure, I guess you guys learned this previous lecture. So there is like Pauli excursion principle. So electrons, the particles like electrons, neutrons, protons, they can't be in the same state. The same state means, so there are some numbers describing the state. So those electrons can't have the same numbers. For example, those electrons can be at the same location with the same speed, with the same energy level. They should be different. So if they are forced to be on the same state, they resist. They don't want to be in the same state. So that generates the pressure. That's kind of degeneracy pressure. So this thing explains the atomic structure, but also we can apply this principle to explain white dwarf or neutron stars or the core of stars. So this picture have been shown a lot of times. So electron degeneracy pressure supports the white dwarf. So when this core shrinks, so if there is nothing happens at the carbon and oxygen core, even though it shrinks, it gets denser and denser, and it cools down because it leaks its energy by photons. So it just shrinks and cools down, and then it becomes degenerate. So electrons become degenerate. So this degeneracy pressure prevents the further contraction. So now gravity can't falls. Now the material can't fall down to the core because the electron degeneracy pressure prevents this contraction. So now the star is balanced by degeneracy pressure and the gravity. So degeneracy pressure, once the star gets bigger, but the gravity holds, so there is some balance. So that is happening in white dwarf. But actually, if it is more massive, so it can. Question? So it can. So if do you mean no? It's not violating. So not to violate the Pauli exclusion principle, it generates the pressure. That's the degeneracy pressure. Is that the question you asked? So if that orbiter is another like another way to describe the thing, but there is also spin. So spin also should be different. So there is another. So we can't no. So it's not violating. So we can't violate this Pauli exclusion principle. So that's why we have degeneracy pressure. So degenerate pressure means now electrons are occupied all the state, so that there is no more state electron be in at that temperature. So we need to go to more detail in quantum mechanics to explain, but the white dwarf doesn't violate Pauli exclusion principle. But later, if the gravity is so strong that even though the electron degeneracy pressure can't support the gravity, then the electron becomes faster and faster, and it reaches the speed of light. I mean, not reaches the speed of light, but the speed of the electron closer to the speed of light, then now electron degeneracy pressure can support the star. Then now neutron becomes degenerate, and neutron supposed to start to support the star. It's kind that's in some sense that's true. Also, the temperature is involved, so it's more like if the only not the position, also the speed also matters for the to describe the state. So I think it's beyond our level. So let's just go further. So this degeneracy pressure supports the star. So as I said, white dwarf is supported by degeneracy pressure, and neutron star is supported by neutron degeneracy pressure. And when stars form some core, helium core, carbon core, or iron core, when there is no fusion, when there is no burning, and they are also supported by degeneracy pressure. So if there is no fusion, if there is no thermal pressure, the stabilizing pressure is degeneracy pressure. And actually, our body is degenerate too. Our electrons in our body is degenerate. The electrons on Earth are degenerate. Also, the Jupiter, the gaseous planets are supported by degeneracy pressure. So we are much more denser, we are much denser than stars. So electrons are degenerate in very dense material. So anyhow, this electron degeneracy pressure does very interesting thing, because normally stars, if they are massive, their size is large. So if you talk about the massive star, and their size is basically large. But if the stars are supported by the degeneracy pressure, then it gets bigger, then it gets smaller. So more massive white dwarfs are smaller than less massive white dwarfs. So you can see in this figure, so Earth size and if the mass of the white dwarf is same as the mass of the sun, then the size is almost same as Earth. But if the mass of the white dwarf is larger than the solar mass, the mass of the sun, then it's actually smaller than the size of the Earth. So the white dwarf is backward. So more massive, smaller size. So here we use the quantum mechanics to explain stars. So quantum mechanics works in small scale, but also we can use quantum mechanics to explain stars. Physics works. That's basically what this course wants to say to you. So we use physics to explain astronomical phenomena, and that physics we see just equations, but that works. That those equations and those things can explain what happens in the universe or what happens to the star. So white dwarfs are degenerate stars. So we talked about the supergiant. So supergiant phases like further fusion up to iron happens to the massive stars. So their ashes, so their death is different. But white dwarfs is the dead star after helium fusion, after the helium fusion. So when the core doesn't burn beyond carbon and oxygen, then they become white dwarf. So white dwarf is one of the stage of the death star. So there are 3 stages of the death star. One is white dwarf, a neutron star, and the black holes. So here we are talking about one death stage, which is white dwarf. So lower mass stars end up white dwarf. So this is the first detection of the white dwarf. So Sirius A is the brightest star in the sky. So we didn't know this Sirius A has a companion, but it turned out it has a companion. That companion is white dwarf. White dwarf is very hot. So it's, for this case, Sirius A is about 10,000 Kelvin, but the Sirius B is 30,000 Kelvin. It's hotter, but it's very, very tiny, so it looks fainter. But both stars are very bright in X-ray, so we observed this binary system using X-ray telescope, and we saw this small white dwarf companion of this Sirius A. Sirius A is this and Sirius B. So in X-ray, Sirius B is brighter. But in optical, Sirius A is brighter than Sirius B. So as I said, only lower mass stars can end up as white dwarf, because white dwarf is supported by electron degeneracy pressure. So electron degeneracy pressure supports the star if the mass is not high enough. So if the mass is very big, then electron degeneracy pressure can support the gravity. The gravity wins over the electron degeneracy pressure, so the star or the core shrinks. But this case, so the first mass limit is calculated by Chandrasekhar, and he calculated this mass limit. I heard while he was heading to the UK to do his grad school, and he calculated this on the boat, and then he showed this result to his advisor. His advisor is Eddington. Eddington is also one of the most famous astronomers in history. But Eddington didn't believe his result. But at the end, he won the Nobel Prize by this calculation. So there is a limit mass, which is 1.4 solar mass. So Chandrasekhar calculated this 1-point solar mass using when the star becomes very, very degenerate. When star is not very massive, the electrons are moving with reasonable speed. But the electrons move very, very fast if the gravity is very, very strong, so that the gravity falls. So if the core shrinks a lot, then the electrons are gets hotter and hotter in some sense. So it is moving very, very fast. So if it reaches the speed of light, then electron degeneracy pressure becomes not significant. The electron degeneracy pressure doesn't become significantly, can't support the gravity. So that limit is 1.4. So if the core mass, previously we talked about the mass of the star from 0.4 solar mass to 8 solar mass. That was the initial mass of the star. But at the end, when we measure the mass of only the core, if the core mass is more massive than 0.4 solar mass, then it can be white dwarf. But if the core mass is less than 1.4 solar mass, then it becomes white dwarf. So this is the limit between the white dwarf and the neutron star. Are you guys following? So we have different evolution stage. One is the stellar mass is 0.4 solar mass between 8 solar mass. And they evolve like red giant and supergiant, and they have now carbon and oxygen core. And this core mass is less than 0.4 solar mass. And they can be supported by electron degeneracy pressure. And they become white dwarf. So there is no more fusion, but they are shiny because they are hot. So just they are losing their heat and they can be bright. So eventually they will be faded out when they lose all the heat which it had at the beginning. But we talked about the stars which have more fusion after the carbon and oxygen. So carbon and oxygen and heavier element. And eventually it reaches iron core. And there is a further process. In this case, actually this mass is not less than 0.4 solar mass. So most of their mass is their core mass is more massive than 0.4 solar mass. So their death stage is different. So for this case, it's like a neutron star or black hole. And also it is calculated, we can calculate the limit between neutron star and black hole using actually the same calculation. We get this limit. So, but this calculation is beyond our scope. So just this mass is important to distinguish it the later evolution stage, and that mass is calculated by Chandrasekhar. So this is a simplified version. But now, and people measured some star we call novae, and the novae means new star. So historically, when people observe the sky, and one day the star becomes very bright. And this star is very, very bright for a few days for a week. And then later, it gradually faded out. And now, and after a month, we can't see that star anymore. So it's kind of new star. So people in the past called this star novae. But in reality, actually, this star is not new. So this star can get brighter for a short amount of time because of some process. And we will see this process, but can you guess why these stars can brighten for a short amount of time? Like why it happens? No. So to become novae, we need something else. So to make a star bright for some amount of time, we need something else. So this is a cartoon for novae. So actually novae, it means new star, but it's very old star. So this white dwarf, somehow it has companion. So this is not very good picture. So there is a white dwarf, and there is companion. But this companion also goes through all the evolution stage. So it fuses hydrogen, and when the hydrogen fusion stops, and it has a hydrogen burning shell, and that heats up the envelope, so the envelope becomes bigger and bigger and bigger. So when this star gets bigger and bigger, it reaches some region where this star can have influence on this matter via gravity. So this star has some gravity, and this star, the companion star gets bigger and bigger. So these materials are loosely bound. So they are not very associated with this star, but also this star affects this material via gravity. So there is some gravitational attraction. So this matter goes to this star briefly. So it makes white dwarf bright. So this picture is a lot better than my picture. So this is white dwarf, and this is the later stage of the star. So it gets bigger and bigger. And this material is accreted to this white dwarf. And when accretion happens, this white dwarf can be luminous. Actually, that makes more luminous the white dwarf than fusion. So this accretion process makes star brighter than fusion makes star. Fusion makes star bright. So let's see better animation here. So just start with this, just to remind you to start with this animation. So the lower mass stars go through all the evolution stage, and after helium burning, it lost all the material on the envelope, and it loses all the envelope, and that is the planetary nebula stage. And Mark will talk about that planetary nebula next time. And then the white dwarf, the core becomes white dwarf. So the envelope, all the material, these are blown away, and the core is remain there and is faint. So if we have the binary star, so one star is much more massive. So let's say this blue star is more massive, so its evolution happens much faster. And then it becomes white dwarf. And the lower mass stars, its evolution goes slowly. So as we said, more massive stars burn hydrogen quickly. So for other states, it's same. So more massive stars evolve very quickly compared to the lower mass stars. So when these massive stars become already white dwarf, these other stars were normal, but later it becomes bigger and bigger, and this material is going to accrete to this white dwarf, and the white dwarf gets shiny. What? So the bigger one is not like quite explode. The bigger one, what it did was, so this. So at the begin, so the bigger one goes through this process more quickly. So after helium burning, and it has carbon and oxygen core, and the shell, there is a helium burning shell. So let's stop here. So there is a helium burning shell. Also, outside of the helium burning, there is a hydrogen burning shell. So there are two sources hitting the envelope. So this envelope gets bigger and bigger. So they are loosely bound. And now there is no more heat source, and eventually this envelope just blown away, because this helium makes this carbon core just bigger and bigger, and no more heating source, and just this shrinks and the outer parts are blown away. So that's a planetary nebula. So at this stage, all the envelope part, all the outer material blown away. So we see some shiny planetary nebula, but we actually don't quite exactly know why planetary nebula is very shiny. So there are like 2 or 3 theories to explain the planetary nebula. But anyhow, the planetary nebula is, we know now it's not planet. We just, in the past, people think it is planet. It is planet, so people call planetary nebula, but it's not actually a planet. So this planetary nebula is the later stage of the stars. So but just this term was used in the past, so we are still using this term, but the planetary nebula is the later stage of the stellar evolution. And then after blowing up all the material, the white dwarf is remained. And so that's this case. So this blue goes through all the evolutionary stage very quickly, but this red is less massive, so it evolves very slowly. So when it becomes giant, red giant, so the hydrogen burning shell makes this star becomes large. So the material is not now loosely bound, and that material is accreted to this white dwarf, which has a lot of gravity. So this nova shines by this process, and if the material is not, if the accreted material is not a lot, so only a small amount of material is accreted, then it's just shiny for a few days or for a week, and then it gets faded out. But if the material, a lot of material is accreted, so if the mass of this white dwarf is over 1.4 solar mass, then supernova explosion happens. So supernova explosion will be talked about. I mean, we will discuss supernova explosion next time. But the novae, just for the novae, the white dwarf is accreting only a small amount of material. So it shines briefly, not like supernovae. And also it can occur again, just by accreting material, by accreting small amount of material. So just we see this novae in the sky in this way. So that's so we learned up to novae stage. So later we will learn about the later stage. So this white dwarf and the novae is the end of the stage of this lower mass stars. And if we go higher mass stars, and they go through slightly different evolutionary stage, and they end up different death stars. So the most crucial property of the star to govern the stellar evolution is the mass. So different mass of star goes different stellar evolution process, And also different mass of star has different temperature, different luminosity. So the mass is the most important to get the right evolutionary stage of the star. So that we end up very early, so it's like just 12:15, but this is the lecture note what I have. All the lecture notes I have. Okay, that's it, thanks. And next time the Mark will lecture, and I will see you in the section.